All right, folks, it's time to talk about buoyancy. It's our next topic. So let's have a look here. So the first thing I want students to know about buoyancy is that it is the result of a difference in pressure between the top and the bottom of an object. Now, what I'm going to teach you and them about buoyancy is true whether it's a cube or any other shape, but it's easier to understand this difference in pressure with a cube. So I want you to imagine a cube that's submerged in water. It's got a rope on it where, it's denser than water, so it wants to sink. We're going to draw arrows representing the forces that the water exerts on the cube where, okay, well, remember that water pressure, or in all pressure, forces are perpendicular to the surface, pointing into the surface. So there's a little bit of pressure on the top. But there's a lot of pressure on the bottom because this is deeper. Remember, pressure is density, gravity, height. If you want to add a pressure to the atmosphere, you can. But the depth, I meant to say, the deeper you are, the more pressure there is. On the sides, I want my students to draw short arrows when it's not deep and longer arrows when it is deep. But these two things cancel out. All right. So how does the fluid pressure cause the buoyancy force? There is the bottom of the cube is deeper than the top of the cube, right? So there's more pressure pushing up than pushing, down, okay, resulting in the water exerting a net upward force. Okay, now the basic equation for the buoyancy force is this. The force of buoyancy force, that is the density of the fluid, the density of the surrounding fluid, okay, times the volume under the fluid line. So that's the volume of the object below the fluid line. So in this case, it would be the entire volume of the entire object. But if the object was floating, the volume underneath would be just this much. Just that much is all that would count there. And then times gravity. Now, I want to show you where this equation comes from. So if you'll allow a brief aside here, let me show you where this equation comes from. So first, I want you to imagine this purple object, and let's just make it a cube, although this works just as well for anything else, okay? And this is going to be the area of the top. And let's just say that this is the height of the cube. Well, I don't want to use H because I'm going to use it for something else. Let's just call this L for length. And then this depth is going to be A, and this depth is going to be B. The depth at the top is A. So the pressures on the top, is going to be the pressure of the atmosphere plus density gravity times this depth, which I'm going to call A. And the pressure on the bottom is going to be the pressure of the atmosphere plus density gravity B, the depth B. Now, what is the force on the top going to be? The force on the top is going to be the pressure on the top times the area. So that would be distributing the pressure of the atmosphere times the area plus rho G, the A depth times the area A. Now, what is the force on the bottom? That'll be the pressure on the bottom times the area. So that's the pressure of the atmosphere A plus rho G, the B depth times the area, right? I'm just taking these and multiplying by area. Okay, so what's the net force of the fluid? It's going to be the force on the bottom minus the force on the top. So watch what that's going to look like. The force on the bottom, pressure atmosphere A plus rho G, the B depth times the area, minus pressure of the atmosphere A. So notice those terms cancel. You could have just done gauge pressure the whole time, plus rho G, the A depth times A. Hey, let's factor out. So you get rho G, B minus A times the area. Do you see that? Do you see how the area and the rho and the G cancel out? And remember, this is the rho of the fluid the whole time. It's the fluid's density, not the object's. That is the length L. B minus A is the length L. So this is density of the fluid, gravity, length times area. That's the volume that's underneath. that's the volume that's underneath, which is all the volume. Now, if you will tolerate one more thing, which is the orange object. The orange object floats. Let's say that a length h is below the water, right? So the force on the top is the pressure of the atmosphere pushing down on top times the area of the top, okay? But the force on the bottom will be the pressure on the bottom times A. So what's the pressure on the bottom? That'd be the pressure of the atmosphere plus density, gravity, H. That's the density of the fluid, all times the area. So the net force on bottom minus force on top. Okay, what's the force on the bottom? I'm going to distribute P atmosphere times A, rho GHA, the rho is of the fluid, minus P atmosphere A, that's the force on the top. We subtracted them. Again, the atmosphere doesn't matter. But what is this? That is only the volume that's physically below the water line. So that's where this equation comes from. It's actually just a difference in two forces due to the two different pressures. Whether you show that to your students or not is your business. All right, now the force of weight is mg, but you may remember that mass is the density of the object, which I'm going to call rho O, not zero, but rho O, times the volume of the entire object, of the whole object, right? So if I plug that into here, then the force of weight is also density, volume, gravity. But watch out. Buoyancy is the density of the fluid times the volume under the fluid times gravity. Weight is the density of the object that's being pulled down by gravity times the volume of the whole object times gravity. So we're going to need to use this for weight sometime. So don't be surprised if for weight I put density, volume, gravity. And by the way, wait a minute, Friendsley, isn't this a mass times gravity also? Isn't this a weight? Yes. This is the weight of what's called the water displaced or the fluid displaced. What do you mean when you say displaced fluid? It's the fluid that would be in this volume if the object was not there. So the water that would fill up this orange volume, the weight of that water is the same as the buoyancy force. The weight of the water that would be filling in this space, but is not because the object is there instead, the weight of that water is the buoyancy force, and that is Archimedes' principle. Archimedes' principle is that the buoyancy force is the same as the weight of the water that had to get pushed out of the way to make room for the thing in the fluid. We call that fluid displaced. How much fluid would be in that volume except that there's something else there like a boat or a block or a square or whatever kind of thing, cube. Okay, a tank is filled with a density, fluid density rho F, object mass M, volume V, and density rho naught is placed in the fluid halfway between the surface and the bottom. Describe what happens to the object when it's released from rest each together. The object is less dense than the fluid. Okay, so here's a free body diagram, and we're going to have the force of buoyancy, which is density of the fluid, volume, which is all the volume because the whole thing is under the water gravity, and then the force of weight, which is density of the object, volume, gravity, but the density of the object is less than density of the fluid. So the force buoyancy is greater than the force weight. The object accelerates up. On the other hand, if the object's density, volume, gravity makes force weight, and force buoyancy is density, volume, gravity, but of the fluid, not the object, then if the object is more dense, then the weight force is greater than the buoyancy force, and the object accelerates down. By the way, don't ever have unbalanced forces and let your students say, oh, the object's going to move down, the object's move up. Always correct them and make sure they say, no, the object accelerates up or down. They need to not think that force and motion is force and acceleration. Not force and motion are related, or else they're going to screw up Newton's laws. Okay, and then here, the force buoyancy is equal to force weight, so we call this neutrally buoyant. And if the object is released from rest, the object stays at rest. So the up here and down here, the force buoyancy, density of the fluid, volume, gravity, the force of weight, density of the object, volume, gravity. The two densities are the same, so it's neutrally buoyant. And that's something that's important for like fish and scuba divers is to be neutrally buoyant, or else you sink to the bottom and you float to the top. All right. Derive an expression for the object's acceleration. If up is positive, then the buoyancy force is positive. the weight force is negative equals ma, okay? And so the student would say, okay, rho volume gravity minus mg equals ma, right? And so then what you can do is you can say acceleration is density volume of the fluid gravity minus mg over m if you want to do that. But if you replace this m, I'm going to change colors for this. If you replace this m with the density of the object, then it becomes the density of the fluid volume gravity minus the density of the object volume gravity equals, hey, m, that's density of the object volume times acceleration. So mass is density times volume. The volume cancels out. The G factors out, and you get density of the fluid minus the density of the object over the density of the object if you just divide, and you factor out the G equals the acceleration. So the acceleration of an object in water only depends on the density of the water and the object, not on how much volume there is. Isn't that an interesting outcome right there? Okay, briefly explain how submarines control their ability to float or sink between mass, volume, density. Okay, so what happens is that to float, the submarine fills what are called ballast tanks with air, and the air is usually in compressed air tanks, right? Making the average density of the sub less than the density of water, right? So that it floats, right? But then to sink, what you do is you fill the tanks with the seawater, right? You fill the tanks with the seawater. You just open the tanks and let the air out and the seawater flows in. And the density of the sub is now greater than the density of water, and then the sub sinks. Okay? We already talked about this before. We talked about it in the density unit. I just put it here again just as a review, so I'm not going to write it out. Go back to the density video on it. Titanic was made out of steel. Student, when presented, says the Titanic should have just sunk. Why didn't it? Well, because most of the Titanic's volume was just empty air, making its average density less than water. But once the hull was breached by the iceberg, then the water flowed in, took the place of the air, and then the mass of the Titanic became more and more and more and more and more because of the water instead of the air, until the density turned into being greater than water's density, right? Okay. An object with an object density and an object volume floats. Oh, okay, so here's the rule for floating. If you float, the buoyancy force up equals the weight force down, okay? The volume of the object is below the surface of Vf. Write an equation relating these four quantities, okay? So there it is. The buoyancy force up equals the weight force down if you float. If you sink and you reach the bottom, there's an additional normal force. So the buoyancy and the weight can't balance because there's a third normal force that makes all three forces balance. But floating, these two things are equal. Density of the fluid, volume under the fluid, gravity. Density of the object, volume of the entire object, gravity, right? Because this is mass times gravity, I told you. So when you cancel these out, you just get the density of fluid times the volume that's under the fluid equals the density object times the volume under the object. Now, if you want to get the ratio of the volume under to the total volume, you take the ratio of the object's density to the fluid's density. So, for example, the density of ice is 90% of the density of seawater. So that means the density of ice over the density of water is 0.9. But that's also the volume under versus the total volume. So 90% of the ice's volume is underwater, right? So I want students to be able to do that calculation just in their head. A beach ball has about 1% the density of water because of all the air in it. So that means that 1% of the beach ball is under the water when it floats, okay? Let's see, what else? Piece of plastic. Let's say a piece of wood has 75% of as much density as water. Then 75% of the wood will be under the water when it floats, and the other 25% will be above. So that's a powerful shortcut for your students, and I would emphasize that to them repeatedly. Okay, this is a classic. Just tell me what the volume and density of this object are. The scale reads 10 newtons when the object is not in the water. Well, okay, so when you're not in the water, the force of the scale and the mg are the same. So out of the water, I want students to be able to say, oh, yeah, well, the force the scale reads is just mg. 10 newtons equals m times 10. So the m would be 1 kilogram, okay? But in the water, what do you have now? You've got the force of the scale, the force buoyancy, and the mg. So the force buoyancy plus what the scale reads equals mg. We already know that the mg is 10. The scale reads 2. So that must mean that the force of buoyancy is the other 8 newtons, right? I want my students to come up with that real quick, right? Oh, the difference is taken up by the buoyancy. But then I want them to take that and set it equal to the density of the fluid, volume, gravity. For water, the density is 1,000 and gravity is 10. So then the volume is going to be 0.0008 meters cubed. Now, I am going to warn you this. This is very important. Please set up a cube or almost a cube full of meter sticks so students know how much a cubic meter is. Even a bathtub is not even a half of a cubic meter. It may not even reach a third of a cubic meter. Maybe some big bathtubs might be more than half a cubic meter, but not even close to a cubic meter. So students will be like, oh my gosh, what a tiny number. Did I do something wrong? No, okay, this right here is about the volume of 0.008 cubic meters, right? Look at how big a cubic meter is. Okay, now that I have the mass and the volume, I can easily get the density of the object. So this is how we can measure object densities very easily through this process. And there's an activity you're going to see, which is called measuring the density of a misshapen object, of an irregularly shaped object, where they do literally this process right here, okay? A ball that has a mass 2 kilograms, volume 0.01, can float on a lake. Okay, I'm just going to double check that that's the truth. And how am I going to double check that's the truth? I'm going to do a mass 2 over a volume of 0.01. Oh, 200. That's less than the density of water. Okay, calculate the percent of the ball's volume that's below the water. Okay, so the ball's density is was it 2 kilograms over 0.01 meters cubed, which is 200 kilograms per meters cubed. So I'm going to say this is 20% of water's density, right? So 20% of the ball's volume is underwater, okay? And then, now what are we going to do? We're going to hold the ball underneath using a force F. Somebody's pushing down on the ball. There's still the mg force and the force buoyancy, and this is not accelerating. Remember, don't just say at rest. Say not accelerating when you have balanced forces, so students know that something that is moving can have balanced forces too, as long as it's not accelerating. You just have to keep reemphasizing Newton's laws. And by the way, if this is the last unit you do, which is my last unit now that they brought fluids over to P1, you better well believe that I am using it as a reason to review students on their force knowledge, right? Don't do motion, force, energy, momentum, simple harmonic rotation, fluids, and then review. Use rotation and fluids as your review. Trust me, I get good scores because of it. Talk to me some other time about that. Okay, what's the buoyancy force? The density of the fluid, the volume that's under the fluid, which is all of it, gravity, force plus mg. Okay, so the density of the fluid is 1,000. The volume that's under the fluid is all of it times 10. Okay, so I think this is 100 right here. Over here we have the force it takes to hold down plus 2 times 10. So you get F plus 20. So the force, we need 80 newtons to hold down the thing. Okay. The smaller balloon, they have very little mass. So really, if they're being, if it takes 2 newtons to hold another one, then with very little mass, they basically have the force buoyancy and the force holding them down, right? Okay, so the force holding them down. Well, the force of buoyancy is density, volume, gravity. Look what it says, 4 times the radius. Well, what did we talk about way back on the first page? 4 times the radius is 64. That's 4 cubed times the volume. That's true as long as these are similar shapes. They don't just have to be 2 spheres, cube and cube or whatever, okay? Tetrahedron, as long as they're similar shapes, right? Well, that means that this takes 64 times. It's the same fluid, it's the same planet, but it's 64 times as much buoyancy force. So 64 times as much force in the first place would be 128 newtons. That's my argument, and I'm sticking to it. Okay, now for some multi-part questions that remind me of a free response. The raft has a density of 700 kilograms per cubic meter. It's set in a fresh water, and the volume of the raft is 0.4 cubic meters, and the area on the top of the base. So the first thing that you can just deduce, volume equals area times height. So I can figure out the entire height of the raft by just taking the volume, 0.4, and dividing it by the area. So this entire volume is 0.2. So there's a lot of geometry that your students need to be able to do. Okay, second story that I'm going to say is I'm going to ask this. Okay, what's the buoyant force on the raft? This is a misdirection. A misdirection is in physics is why I ask for this, but you're going to give me that's equal to this. For example, calculate the momentum after the collision, and you calculate the momentum before because before and after momentums are the same. Tell me the kinetic energy at the bottom of the ramp, and you tell me the potential energy at the top because they're equal numbers, right? Well, the buoyant force on the raft is equal to the weight force since the raft floats. That's important, okay? So I'm not going to calculate the buoyant force. I'm going to calculate the weight, which is the same number. Weight is mg, and m is the mass of the density of the object, the volume of the entire object times gravity. The density of the raft was 700. The volume of the entire raft was 0.4. Gravity is 10, so you get 2,800 newtons of weight, which is the same as buoyancy force. What about this little height right here? I'm not going to get this height right here. I'm actually going to get this height and then subtract. So how are you going to do that? What I'm going to say is I'm going to say the buoyancy force. Now this is density of the fluid, volume under the fluid, gravity. The buoyancy force is the same as the weight because it's floating. The density of the water is 1,000. The volume underneath, I don't know, and gravity is 10. So if you divide, you get the volume under the fluid is 0.28. 0.28 is under the fluid, right? Meters cubed. So now I'm going to say volume under the fluid equals the height under the fluid times the area, right? Volume is area times height. This is a very important equation. Please do not let your students forget it. 0.28, and the area of the top of the raft is 2. So the height under the fluid is 0.14 meters. So subtracting from 0.2, the height above, subtracting from 0.2, 0.14, you get 0.06 meters. Now, there was a quicker way to do this, so I'm going to show you the faster way. Listen to my logic that's fast. The density of the raft is 70% of the density of water, right? So 70% of the raft is under the water, okay? 30% is above. 30% of the raft is above the water. Well, what's 30% of 0.2? 0.06. Okay, if the average mass of a person is 40 kilograms, what maximum number of people can sit on the raft before the raft is completely submerged? Okay, so if the raft is submerged, right, what are we going to say? That the volume under is equal to the volume of the whole raft. So, assuming the raft is neutrally buoyant and it's about to sink, we're going to say that the buoyancy force equals the weight force. The buoyancy force, density of the fluid, volume, but now it's the whole volume, gravity, and that's going to equal what? Well, there's two force weights. There's the weight of the raft, and there's the weight of the people. Okay, so you get 2,800 for the raft's weight. That's his mg. And then the people is going to be m times g. Let's get the mass of the people. Okay, so what was this? The density of fluid, 1,000. The volume was 0.4. Gravity is 10. So this is 4,000 equals 2,800 plus mass times gravity is 10. Bring it over. 1,200 equals m times 10. That's mass of 120 kilograms. 40 per person, so that's 3 people. All right, so that's the way that works there. Okay, you have a spring. The spring gets 10 centimeters longer when you hang a mass from it. And then when you put the mass in the water fully submerged, the spring retracts 0.2 meters. So now this distance now, or whatever it was, is 0.08 meters, okay? What's the spring constant of the spring? In this picture, the spring force is balancing the mg force. So kx equals mg. The k, I don't know. The x was 0.1, it says it right here. And the mass is 20. So 20 times 10. Okay, so the k is going to be 2,000 newtons per meter. Now, what's the buoyant force on the fluid? Well, there's a couple of ways you can get it. One more difficult way is to say, okay, it's mg. It's now k times the x, but the x is now 0.08 meters and the force buoyancy, and say this plus this equals this. You can do that. Here, I'll do it really quickly for you to just show you. So the k is 2,000, but the x is now 0.08 because of the retraction, right? And then what was the mg would be 200. Okay, so 2,000. Oh, I didn't even do that correctly. I'm sorry. This is supposed to be a plus, and this is supposed to be an equal because up plus up equals down. So 2,000 times 0.08 is 160. So force buoyancy plus 160 is equal to 200. And then the buoyancy is equal to 40 newtons, right? That's really difficult. Can I just tell you? Here's what would have been easier is to say the difference in the spring's force before and after submerging, right? The before and after submerging, the difference in the spring's force before and after submerging is the force of buoyancy. So then the force of buoyancy is delta, the force of the spring, which is k delta x. The delta x is 0.2. So 2,000 times a 0.02, that gives you the 40 newtons also. And that's easier to understand. It's just how much does the spring's force change? Okay, and then what's the density of the fluid? Well, we know the force of buoyancy is density of the fluid, the volume under the fluid, which is all of it, gravity. The buoyancy force we already found out is 40. The density of the fluid we don't know, but the volume was given to us 0.04. Gravity is 10. So if I divide, I get 4, and then I'm going to take 4 over 0.04, which I should do in my head. The density of fluid, wow, that's really not a dense fluid, but whatever. Kilograms per meters cubed. Well, I don't know any fluid that's not a gas. I don't know any fluid at all because gas are way less than that, dense than that, and even liquids like oil are in the higher hundreds. But you want to know what? Let me just tell you one of my philosophies before I end the video here, and you'll see it all throughout the notes and even the example questions, is that students learn the physics better if the problems that they're given have nice, friendly numbers. That's decimals that don't repeat forever, numbers where they can even do the math in their head possibly. Then there's a lot more room for them to learn physics if you do that. And yeah, it results in some unphysical possible numbers. And even my students will call me out on that, where they're like, that person's running at 10 meters per second. That's really fast. I'm like, yeah, that's Usain Bolt fast. But I'd rather have the number 10 that's friendly to you than have a more realistic number like 7.896. And then you're doing the same physics, but you're psychologically worn down by how weird the numbers look. Well, Frensley, do you never do realistic numbers? Yeah, we do. That's what the activities and labs are for. So there's a little discussion of my philosophy for you and why I choose the practice problem numbers that I do. All right. So next video, we're going to talk about my buoyancy lab, and then the activity that basically looks just like this, where you give them a misshapen object and ask them to find the density of it.